Hello, welcome back. We're going to start today looking at Chapter 10, Section 5. We're going to learn how to test convergence at endpoints of interval of convergence. And we're starting off with a very important Part 1, the integral test. Now, I want you to hear clearly, the integral test is covered on this year's AP exam, so this is very important to know. So here we go. The integral test is a very powerful test for the convergence of a series. It won't tell you what a series converges to, but it will tell you whether or not it converges. And it can give you some upper and lower bounds for the series. So, suppose I have some sequence a1, a2, ... an of positive terms, no negatives. And suppose that an is equal to f of n, where f is a continuous positive decreasing function of x for all x greater than or equals some initial positive integer. Then the series and the integral either both converge or both diverge. I think it'll become obvious when I show you a picture. The understanding and the proof of the integral test is quite intuitive and visual. We're going to use the example where the capital N from the theorem is 1, but you could easily modify the proof to make it work for any number. Let's look at the following example. Remember, in this illustration, a1 is the same as f of 1, and in general, an is the same as f of n. Now, let's compare a couple of things. Notice in the left example that the LRAM, a1 plus a2 plus ... plus an is pretty clearly greater than the integral from 1 to n plus 1 of f of x dx because it lies above the curve. And on the right side, let's notice that the sum a2 plus a3 plus ... plus an is lower than the integral from 1 to n of f of x dx. Putting this together, we have the following. Now, this relationship is going to stay true as n gets larger and larger and larger. So let's take the limit as n approaches infinity. Now, of course, as n approaches infinity, so does n plus 1. So we find the following nice little relationship. So we notice here that the integral from 1 to infinity of f of x is trapped between two infinite series, and the only difference between the two infinite series is that the one on the right includes a1 and the one on the left doesn't. Since a1 is finite, it should be obvious that if the infinite series on the left converges, adding a1 to it isn't going to change that, so the infinite series on the right will converge, and then the integral is trapped between two convergent series, so it has to converge. On the other hand, if the integral diverges, then the sum from 1 to infinity of ai will have to diverge because it's larger than a divergent integral, and therefore both series converge. So the series and the integral either both diverge or both converge. Let's take a look at an example of how to apply this. So this series will converge if the following integral converges. Here I'm going ahead and rewriting the 1 over x root x as x to the negative 3 halves, and then following the procedure we learned in Chapter 9 for dealing with integrals involving infinity. So let's continue. So since the integral converges to 2, the series must converge. It will not converge to 2, but it won't be terribly far off it. In fact, if you go back and look at that original series relationship which trapped the integral between a series and another series, you could probably get some idea for some bounds. But the key thing here is the concept that since the integral converges, the series converges. In fact, there's a very nice little reminder of something we worked on earlier called the p-test. So here was the p-test basic. So we worked on this back in chapter 9, and integrals like this converge if p is greater than 1 and diverge if p is between 0 and including 1. And in this case, we were looking at a p-value of 3/2 because this is 1 over x to the 3/2. So we could just tell that this converges because that's greater than 1. Just for the sake of completeness, I'm going to remind you what happened when the integral was from 0 to 1, where everything flips. Now, that 1 doesn't really have to be 1. It can be any positive constant at all. So the rules would also hold, for instance, the integral from 5 to infinity of 1 over x to the p dx would also converge if p is greater than 1, and same kind of thing if it was the integral from 0 to 5, the divergence and convergence rules would still be the same. Here, this is summarized in a chart. Remember, the harmonic series is simply the p series where p is 1, so it's 1 over n. The harmonic series was, of course, the following. We'll talk more about the harmonic series in just a moment, but first, that chart I promised. It's interesting to say use the integral test to prove these because they're all immediate consequences of the earlier p tests that we developed back in chapter 9. So I summarized it in the previous screen, but here it is. Sum from 1 to infinity of 1 over n to the p converges if and only if p is greater than 1. If it's 1 or between 0 and 1, it will diverge. Anyway, back to talking about harmonic series. The proof that this diverges is really quite sweet. The first term all by itself is at least a half. The second term all by itself is at least a half. The next two terms, each of which is at least a fourth, together are at least 2/4, which is at least 1/2. The next four terms are all at least 1/8, so collectively they are at least 4/8 or at least 1/2. I can keep doing this forever. 9th through a 16th add up to at least a half. A 17th through a 32nd add up to at least a half. So this is an infinite number of groups of terms, each of which add up to at least a half, so clearly it grows without bound and it diverges. I've always thought that was a pretty cool little proof. But how slowly does it diverge? How many terms would I have to add up so that the sum adds up to at least 20? I strongly recommend you don't take out your calculator and start adding up 1 plus a half plus a third plus a fourth and waiting till C till that sum gets to 20, because it's a pretty large number. Let's take a look at the following diagrams. So let's let h sub n be the nth partial sum of the harmonic series. So the first thing to notice, for example, h4 would be 1 plus a half plus a third plus a fourth. And it's pretty obvious that it is less than 1 plus the natural log of 4 by comparing the two diagrams. The natural log of x, remember, was the area trapped under 1 over x between 1 and x. So anyway, I want to know the following. I know that in general, hn is less than 1 plus the natural log of n. So 1 plus the natural log of n is greater than hn, which is the nth partial sum, and I want to know when the nth partial sum gets greater than 20. Well, solving this, I get natural log of n is greater than 19, and exponentiating both sides, I get n is greater than e to the 19th. And e to the 19th is pretty damn big. In fact, e to the 19th is around 178,482,300. So you would be sitting there entering numbers into your calculator for quite a while. And you'll notice that this is only an approximation. This is only a lower bound for how far you have to go. You have to actually go a fair amount further. So with that, we conclude part 1 of 10.5. The integral test, again, this is on the AP exam content this year, so please make sure that you get this down. I hope everyone is well, and stay healthy and stay entertained, and we'll ride this out together. Bye-bye.